So, let us get ahead with the study of statistical mechanics. Just wanted to make 2 points clear. One is that when you study statistical mechanics from a book, it is usually very verbose, which means that lot of reading needs to be done, lot of description is given, sometimes through examples or through words, and you do not feel it so attractive to read through all these verbose description. But you have to understand one thing, that the author is not present in front of you. So, whatever his thoughts are, the way he wants to clear up the concepts and confusions, etc., that he has to do it by description, and that is why often it gets verbose, and students find it that they are too much to read and feel a little disappointed about that. But that is a part and parcel, and you should read books, and there are extremely good books on statistical mechanics. I will just list a few of them. We have a very good book called Patria. Patria, then there is a good book by Huang. There is a very nice book by Jem Setna. Then there are these Macquarie. I guess this Q has to be capital, and so on. And there are other books as well, but these are some of the books that are very good, and they give you a lot of insights into the study of statistical physics. However, each has a distinct way of presentation. So, my suggestion would be to stick to one book and learn the subject well, and in fact, Patria is a very good textbook which is accepted all over. So, you may want to have a copy of this and study along with the lecture notes that you have from this course. The second thing is that you would often find me writing on the board, on this digital board, and this is to make sure that you do these as I do it in front of you. So, you do it on your own, and a lot of calculations will get clear when you do these calculations by hand without seeing either the lecture videos or some of the books. Try to do it themselves, and this is one of the reasons that I some of the derivations where I need to speak and give you the steps of derivation, I do that instead of just showing you the slides, which will have lesser effects than what is intended here. All right. So, we will start with ensemble theory, and the application of statistical mechanics relies on the study of ensemble of systems and not a single system. In fact, it is often difficult to study the properties of a single system, whereas the properties of similarly prepared, this word is important, similarly prepared systems is possible and often easy to interpret. I will give you an example that if you are an avid follower of cricket, you would know that somebody talks about either the strike rate or his average scores in an innings for a batter, and that is often taken when he has at least played 20 matches or 50 matches and so on. Anything lesser than that, there is no point in talking about averages. Okay. So, a large number of innings or large number of matches are being considered when you talk about averages and so on. So, these are in this technical jargon, it's they are called as ensembles, or these will know what ensembles are. But let me first take you to some of the prerequisites of ensemble theory. One of this is called as phase space, and the other is called as a macrostates, microstates and macrostates. Okay. So, we for that let us take this phase space, And in classical mechanics, we are quite familiar with the configuration space and the momentum space. In fact, the configuration space that is given by x, y, z or r theta phi and so on, they can be solved by solving Newton's law of motion subjected when a particle is subjected to certain force. And this is widely used in all branches of physics, not only in classical mechanics. And momentum space description is often suited in various fields of quantum mechanics, or say for example solid state physics, when a system has translational periodicity or translational invariance, that is the space is homogeneous, then k is a good quantum number or is a conserved quantity, and that is why we resort to the momentum space or k space. Here k means p equal to h cross k. Okay. So, this configuration space is, as I said, just represented by x, y, z, and the volume of this space is given by dx, dy, dz, as you can see it here in this diagram below. And so, it is a cube, it is a small cube, and that each of the sides are dx, dy and dz, and with respect to certain origin, there is a point that is at the center of the cube, which has a position which is x, y and z, which is not shown here, but that is what it is. Let me try to show this here. So, this point that you see here is x, y, z and so on with respect to certain origin. So, you have built up a volume around it, and this volume has the volume is equal to the dx, dy, dz. Similarly, in the momentum space, once again we have this momentum given as say px, py and pz to be the center of this this cube is has coordinates px, py, pz in this a plane defined by px, py and pz, and you have constructed a volume around it, and it is often written with a d tau, or we can also write it with dv, which is equal to dpx, dpy and dpz. Now, what is phase space? So, phase space is a mathematical concept of constructing a 6-dimensional space which incorporate both the configuration and the momenta coordinates, which means that for a single particle it will have 6 coordinates to go along with, and these 6 coordinates are x, y, z and px, py, pz, and now the elementary volume is a 6-dimensional quantity, which is dx, dy, dz, dpx, dpy, dpz and so on. So, this is a 6-dimensional plane or space for one particle, and since we consider n particles and n to be of the order of Avogadro number 10 to the power 23 or 10 to the power 24, the space is 6n dimensional. So, even if it looks like that, we have artificially enhanced the dimensionality in which we are going to study, but this makes a lot of things quite simpler, and which is what we are going to see. So, in a general sense, instead of using x, y, z, one uses q1, q2 up to q3n coordinates. N stands for the number of particles, as I said. There will be p1, p2 and p3n, where q's are called as the configuration coordinates, and these are the momenta. And why do we shift from x, y, z to q1, q2? That is because these are called as the generalized coordinates, and how generalized coordinates differ from ordinary Cartesian or ordinary this configuration coordinates, because these take into account the constraints that the system possesses. Okay. So, the system may possess certain constraint, say there is a sort of dumbbell which is in space, which means that there is a constraint that the distance between these two weights they always remain fixed, and this may actually rotate, or they may undergo translation, but with respect to one, the coordinates of one of the masses, let us call this as mass m1 and m2, the distance is always constant, and this is a constraint of the problem. So, these QIs, they take into account the constraints. All right. So, the state of the particle, this is very important, the state of the particle is denoted by a point in the phase space. So, the state of the particle means or the state of the system, for example, is a point in the phase space. So, 6 dimensional space or 6n dimensional space, if you put a point there and that point is your system, maybe a classical ideal gas, that is a sort of a representation of your system in the phase space. And of course, as the time evolves and the molecules of the gas would be moving around due to the kinetic energy present in them, this gas will execute a trajectory in the phase space. So, that could be a line, or that could be sort of a trajectory that we will see soon. Okay. Though it is a purely classical concept, because we are talking about energy and momentum at the same footing, and which is prohibited by quantum mechanics owing to the uncertainty principle, which says that if you really want to precisely determine the position of a particle, then the momentum uncertainty, that is a measurement of momentum, yields a very huge uncertainty, and this is called as the uncertainty principle, and delta x into delta px will be of the order of h cross, which of course we can neglect in classical mechanics, but h cross, which is, or h, say for example, h is the Planck's constant, it cannot be ignored in quantum mechanics. However, still if you want to have an analogy and want to sort of carry on some of the ideas of classical mechanics to quantum mechanics, then these points that we talk about in this phase space can be represented by a small volume of the order of h cube, and that would sort of let you at least establish a correspondence or an analogy. So, this evolution of the particle's trajectory are given by these equation of motion. These are called as the Hamilton's equation of motion, where the time evolution of the coordinates which are called as a qi, the generalized coordinates, and the generalized momenta here, which are pi, are given by del h del pi and minus del h del qi, where h denotes the Hamiltonian of the system. All right. So, if you solve them, they give you how qi and pi they evolve in this phase space. Okay. So, a surface in the phase space is defined by the locus of all the phase points that satisfy this relation, that h of a qp, which is the Hamiltonian, which is a function of this generalized coordinate and the generalized momenta, that would give you the energy, which is a constant. So, E is the energy of the system. So, that is the surface in a phase space, and this surface either can be a hyper volume, or it can be it is often called as a hyper cube, or hyper surface, or hyper volume, and so on. So, this is a generalization of this volume from say 3 dimension that we are aware of to larger, much larger dimension. Okay. Often we find that it is much better not to fix a value of energy to be taking a single value, that is, you relax the condition that the energy is strictly a constant, a value E, but you allow a small variation of energy of the system. And say the system can have energy between some E minus delta to E plus delta, where delta is a has a dimension of energy and is a small quantity as compared to E. Okay. So the trajectory of the system will be restricted in a hyperspace which is defined by these two limits. Okay. Let me now sort of show you the phase space. How does it look like for a couple of simple examples. And say the first example is a mass m is confined to move in one dimension. Okay. So, and it is a free mass or free particle. Okay. So, you can add this thing, it is a, or we will just add it here, it is a free particle. And the moment I see it is a free particle, it means that the energy is given by E equal to p square over 2 m, because it is free. The only energy that it has is a kinetic energy, and p is a momentum, and m is a mass, as it has been said. Okay. So, this tells you that if you want to know the phase space of this particle, which is confined to move in 1D free particle. So, this p becomes equal to a plus minus root over of 2 m e, and that gives you that there are these two energy values. So, this is your now we can call it x or q, whatever you want to call it. And so, this is plus root over 2 m e, and this is minus root over 2 m e, and this is the p axis. So, it is a p q plane, and we are just talking about one particle. So, this is the phase space of this particle. So, they are restricted between two values of p, which are plus root over 2 m e and minus root over 2 m e. And just like as we have said, if you give a little bit of energy variation, so that they are really allowed to be confined in this region and similarly in this region, then this is of course of the width. This is a delta p, and this is delta p as well. And so, the total phase space is for this particle, there is just one particle, as I said, and that too in one dimension. So, things are extremely simple. So, total phase space available to the particle is equal to 2 into delta p into root over 2 m e. The 2 you understand, because there are 2 of them at plus root over 2 m e and minus root over 2 m e, and delta p is the width. So, that shaded area is the phase space that is available to the particle to move in. Okay. Second, the more familiar example that is there everywhere. So, for a 1D harmonic oscillator. So, what I mean by a 1D harmonic oscillator, it could be a mass spring system, say for example like this. So, there is a rigid wall which has a spring attached to it, and there is a mass that is attached to it, and this is of spring constant k, or it could be a pendulum, say, which is made to oscillate in this vertical plane. So, the energy of that is given by the p square over 2 m, but now it is not only p square over 2 m, there is a half k x square energy which is associated with the spring. Let us just talk about the spring mass system. This is equal to the total energy. Okay. So, if energy is a constant, then of course, you have this it varies with p and x as p square over 2 m plus half k x square. Now, what I do is that I will do like this, root over 2 m e whole square plus x square by root over 2 e over k square, that is equal to 1. I will write it in this particular fashion, and this is nothing but the equation of an ellipse, and this has in the p x plane. Remember that we are writing it x back to the original notation for the configuration coordinates. One could write it as q as well, just to loosely writing it as half k x square. So, this is the p axis and this is the x axis or q axis. It will be a ellipse which has a semi major axis as root over 2 m e square. So, this is like a p square by a square plus x square by b square. This is equal to 1. So, you have a semi major axis and a semi minor axis there, and again if E is made to sort of vary between some E plus delta to E minus delta, we can write it as. So, this is the available phase space for the particle. Okay, so, this is the phase space available is between these two ellipse, which this is E plus delta E, and say this is E minus delta E, or just E, that would be also be fine. Okay, but we just write it in a symmetric fashion. So, it is between E plus delta E and E minus delta E. Okay. So, these are the concepts of phase space that you often get. Let us just look at the second thing that we have talked about, that is this microstates and macrostates, as you see at the bottom of this slide, and let us try to explain what are these macrostates and microstates. Okay. The state of a system is completely specified by the macrostates. Which means that it could be the pressure, volume and temperature of a system, or the energy, volume and number of particles of the system, and so on. So, they sort of tell you that this gas has a classical ideal gas has a certain pressure, volume and temperature, or certain energy coming from the momentum. So, make sure that this capital P is used for pressure throughout our discussion, and small p is momentum. So, please make this distinctions in your when you read it or when you work out things. And now, this state of the system described by this PVT or EVN, they say nothing about the internal structure of the gas, it just tells you about the state of the gas. And if you sort of, if I have to give some examples, so let us say that we have a P, V and T, and there is a certain point which corresponds to P0, V0 and T0 of a gas. Now, these are the macroscopic parameters that specify the state of the gas, that you have made a measurement and you have got a value which is P0, V0 and T0. Okay. But this particular macrostate may correspond to very large number of microstates. That is, suppose we talk about a gas like this. We will just draw a few boxes here, and only look at say for example, a few particles, and this is one particle marked by red, and there is one particle marked by blue, and there is say one particle marked by green. Okay. There are of course Avogadro number of particles, we can't draw all of them, but we just simply draw 3 particles, and in this diagram, schematic diagram that you see, it represents the same gas with P0, V0 and T0. But however, these particles which we have marked by red, blue and green, they occupy different configurational position, or you can say the position in the phase space. We are just showing it inside a box. So, it might give you a feeling that we are only talking about the configuration space, but that may not be true. It is we may be talking about the phase space. So, in the phase space, these 3 descriptions of the gas are distinct. So, they correspond to different parts or different points in the phase space. So, let me draw that phase space as well, and so there is a P and sorry, this is momentum. So, we will call it as a P, and now we go back to our original generalized coordinates and so on. So, this may be the trajectory of the particle, and this is your A, let us call it as A, and this is B and this is C. So, this could be B and this could be C. Okay. So, A, B and C, this correspond to different points in the phase space. So, these are this is the same gas as we have in A, B and C, but their internal structures are different, and these corresponds to different microstates. Okay. So, and every point on the phase space trajectory will give you a different microstate. Okay. And so, a macrostate in general is comprises of very large number of a macrostate comprises of a very large number of microstates. Okay. Let me give you another example. So, let us have a spin configuration, or simply you can talk about magnetic moment. Let me just go back and just reflect one more time on this, the same slide that we have been on. You might wonder that we have of course colored the some molecules of the gas by some red, blue and green. Is it really plausible? I mean, is it sort of can we do that? Are we allowed to do that? And the answer is that yes, in classical physics all these particles are known to be distinguishable. We can label them as per our wish, but however, as soon as you go to quantum mechanics or quantum physics, the particles become indistinguishable, and indistinguishable particles cannot be simply mark them by red, blue and green. We will have to follow that procedure of indistinguishability, and we will do that when we come to quantum statistical physics. Okay. Coming back to the second example that we say, let us talk about a magnet, and there are a number of spins, and let me sort of this is so there are 4 magnetic moments or spins, if you like, they are pointing up and 3 are pointing down. So, I can have this, and this is another configuration of the same thing, and this is another configuration of the same thing, and there are many configurations that one can find or one can write down. So, the same macro state with the net magnetic moment to be say 1 unit, because there are 4 up and 3 down. So, there is eventually 1 magnetic moment upward, or pointing upward, and so they correspond to all of these configurations, they correspond to the same macro state. But however, each one of them is a distinct microstate. So, this is one microstate number 1 and this is microstate number 2 and this is microstate number 3 and so on, and we can put a large number of combinations with here, and each will give rise to a distinct microstates where the first spin to the the seventh spin are ordered either up or down to give you the same net magnetic moment, which is 1 unit pointing upward. Okay. So, let me give you another example of say walking in a room. Imagine yourself that you are standing in a square room or rectangular room, it does not matter, and you are right here. Okay. And you are asked to go from point A to a point B. Okay. And so the macro state would correspond to these two extreme positions that one has to go from A to B, but then you see that there are so many microstates present. You can go from this side to this, and then this to this. You can go like this, you can go like this, you can go like this, and you can go like this, and you can go like this, and you can go like a large number of ways. So, the number of ways that you can go or rather walk in order to reach from the point A to point B, they denote the microstates. So, these are the microstates of the system, and the macrostates are A to B is a macrostate. Okay. I think it is by now clear that these each macro state, which is a overall course description of the system, that corresponds to a large number of microstates. And these microstates are very important because these microstates will eventually be related to the entropy of the system, as we will see. You take the log of the number of microstates and multiply it by the Boltzmann constant, you get entropy of the system. So, that tells you that a ferromagnet which is represented by only one configuration where all the spins are pointing up. I mean, what I mean by ferromagnet is that all the magnetic moments are pointing in the same direction. This has there's just one way that it can be done, and so this has a number of microstate is equal to 1, the number of microstates equal to 1, and when you take a log of 1 you get a 0. So, the entropy of the system is 0, and by now we know that the entropy is related to the disorder present in the system. So, this system is least disordered, and we know that it is an ordered system. An ordered system, completely ordered system is not a disordered system, and that is why the entropy is equal to 0. So, I will stop here and thank you.